a few more examples of these types of improper integrals. So this time we have 1 to infinity of ln x divided by x dx. And obviously it's improper because of the infinite integral or the infinite limit. So we have the lim as c approaches infinity, integral from 1 to c of ln x divided by x dx. This is a pretty basic integral. It's not really basic, but it's a u sub. So let's let u be equal to ln of x. And the derivative of natural log is 1 over x dx. And clearly, what we can see is that this is going to be a pretty easy u sub. So we get lim as c approaches infinity. I'm just going to change the bounds to a to b, just use some dummy variables. Natural log is u. Dx over x, which is exactly the same as this right here, is going to be our du. Right? Now we can integrate. We know the antiderivative of u is u squared over 2. So we end up with the lim as c approaches infinity, u squared over 2 from a to b, which is the same as the lim as c approaches infinity of the natural log. So let me make that look like a real lim as best as I can. So lim as c approaches infinity of the natural log of x squared divided by 2 from 1 to c. And now we could just substitute c and substitute 1. So this is going to be the limit as c approaches infinity of natural log of c squared divided by 2. And then we could just substitute the 1 back in. So ln of 1 squared divided by 2. So some good news. Natural log of 1 is 0. All right. And we have 0 squared over 2, which just cancels that out. However, the natural log function as x goes to infinity, or in this case, c goes to infinity. So this is about what our natural log function looks like. And we know as x approaches infinity for natural log, that means y also approaches infinity. So the limit as c goes to infinity of ln c is going to be infinity. So we get infinity squared over 2. All right. And I know that's not the right way to write it, but maybe thinking about that might be helpful. And we know that this is just going to turn into infinity, right? Because if we square infinity, we divide it by 2, it's still going to be infinity, all right? Now, what that means to us is that this integral is divergent, okay? So anytime you get like an infinity or a negative infinity, that means that the integral diverges, all right? To verify this, if you want to check in Wolfram alpha, what you would do is you would integrate the natural log of x divided by x as x goes from 1 to INF if you're typing it in. And we just go ahead and hit enter. And what you'll notice is that eventually it's going to say this integral does not converge. Okay, so be wary of that. Okay, we haven't necessarily seen any examples that do diverge, but this is one of them. Okay. That doesn't mean that every single integral with an infinite limit diverges, okay? So we have another infinite limit here. So we have negative infinity to 0, x e to the x dx. This is a little bit tougher because not only is the limit negative, or I'm sorry, the discontinuity or the improper component. So c approaches negative infinity, all right? But the integration isn't necessarily going to be a u substitution. Okay, so we have lim as c approaches infinity, c to 0, x e to the x dx. To be able to integrate this, we're actually going to have to use a integration by parts. U is x, and dv is e to the x dx. Okay, and the reason you know it's integration by parts is because, well, if you try u substitution, it's not going to work too well. Okay, in fact, it's not going to work at all. Okay, so now our du is just dx, and our v is e to the x. All right, so remember, to go from here to here, you take the derivative And to go from here to here, you integrate, okay, to get rid of dv, okay? Our formula for integration by parts, uv minus integral v du, all right? And I just try to do like one of these things to try to help me to remember. So uv is going to be x e to the x. So this is going to wind up being the limit as c approaches negative infinity. And this is going to be x e to the x, okay, from c to 0, minus the integral of v du, which is going to be e to the x dx. All right. Now, the good news is e to the x dx is the easiest integral to evaluate because we can't get it wrong because we know it's e to the x dx, or it's just going to be e to the x. So lim c approaches minus infinity, x e to the x minus e to the x from c to 0. All right. Now be careful with this. Most of the time, 0 is the lower bound, but in this case, it's the upper bound. So let's substitute that in first. So by our fundamental theorem of calculus, we have 0 e to the 0 minus e to the 0 minus our limit as c approaches negative infinity of c e to the c minus e to the c. All right, so easier part first, okay? Over here, 0 times e to the 0, that's 0 times 1, which is just 0. This just turns into negative 1, okay? So that's negative 1. Now, this limit is a little bit sneaky, okay? So think about this. If you're substituting negative infinity back in, okay, this would actually be, and think about this, this would be negative e to the minus infinity for this one, which is really negative 1 over e to the infinity, all right? E to the infinity is just infinity, and anytime you divide by infinity, it's 0, okay? So as long as it's a constant on top. So that makes this go away, right? But what about c e to the c, all right? So what a way that you guys can try to resolve this is by trying to graph the function and then looking at the long-term behavior of the function as it approaches negative infinity. Okay, so on a graph here, let's just graph x e to the x and see what happens. All right, pretty quickly, it looks like that it's approaching negative infinity, okay? And in fact, what we can do is, so we can say from, let's just say negative 100 to negative 90. All right. And what you'll notice is that as it's approaching, and these values are extremely small, right? What you'll notice is that it's approaching 0, okay? And certainly what you could do is you could just go ahead and keep plugging in numbers for a table of values as another way. But clearly what we can see is that it's going towards 0 as c approaches negative infinity, all right? So this actually goes to 0 as well. And we already know that this is going to be negative 1 from here. So we get negative 1 minus 0 plus 0. All right, not that it matters. And so ultimately, this just winds up being negative 1. Of course, if you don't trust me, just go into Wolfram Alpha and you can integrate can't spell it apparently. So x times e to the x from negative INF to 0. All right, and if we evaluate this, we get negative 1 out of that. Okay, so certainly, guys, again, use Wolfram Alpha to make sure that your answers are correct. But of course, during the examinations, you have to know how to do everything by hand as well, like this. Okay, so this is a little bit more important than being able to just check the answers. All right, so we do have some more examples coming up. We've looked at infinite discontinuities, and we've looked at discontinuities at endpoints, but we haven't looked at internal discontinuities. So we're going to get there. Okay, so just for now, just make sure you're good with these before moving on.